All right. Hello, everyone. So this week we're going to start talking about compounds and chemical bonds. Right? We spent the first 2 weeks introducing atoms, talking about some properties of atoms, the individual elements. Now we'll start talking about compounds, which is bonding between different elements. Okay. So first we need to do a little bit of background with just talking about matter and matter classifications and properties. So this first idea is chemists will either classify matter as either being a pure substance or a mixture of substance. A pure substance is something that is sort of like uniform in composition. It would have its own distinct properties, smell, color, taste, etc. A good example, a very simple one would be something like water would be a pure substance, has its own properties, distinct properties, as well as like a particular metal. So something like iron, if you had a block of iron, that would also be a pure substance. Okay, a mixture would be if you have a composition of two or more substances, and then like they could be in varying proportions as well, right? So you could imagine I had iron filings that I put into my water. They're just kind of floating around. I can change the proportion of iron to water. That would be a mixture. These are relatively intuitive concepts. Okay, there is a further designation that we have when we're talking about mixtures, and those would be either homogeneous or heterogeneous. Okay, a homogeneous mixture is uniform throughout, right? So meaning that if I had like this sort of a cup of this mixture and I took a sample from the top and I took a sample from the bottom, are they the exact same? That would be a homogeneous mixture. So for example, if I took a glass of water and dissolved some sugar into it, there would be equal amounts of sugar floating around in the top as there would in the bottom. It all looks the same. This is a homogeneous mixture. A heterogeneous mixture would be if it is not uniform, right? So the previous example where I had those little iron shavings in my glass of water, they'd kind of settle down to the bottom. So there wouldn't be as much at the top as there would at the bottom. You could also sort of, if you had like a sand and water mixture, that would also be a heterogeneous mixture. Something that you could think about it as simply as, again, if I take a sample from the top and I take a sample from the bottom, are they going to be the exact same throughout? Another classification of matter that we have is a substance. All substances could exist as either solids, liquids, or gases, right? So we have an intuitive understanding of this, but let's talk a little bit about it as well. A solid is of course something, like your cell phone's a solid, something that you could hold very easily. It keeps its shape, right? The reason for that, if we're going down to like a molecular level, is because you have a tight packing of the atoms or molecules within a solid, right? They're kind of rigidly frozen in place when you have a solid, these two molecules that are next to each other. A liquid does not hold its shape. It'll conform to the shape of whatever container it's in. And that's because, like a solid, these molecules are packed together really tightly. However, unlike a solid, their position is not fixed. So they're constantly sort of like tumbling and rolling around over one another. Their neighbors are constantly changing. So these molecules are bumping up next to each other, and then this one goes and sort of talks to some other molecule, different from a solid where everybody's position is fixed. Everybody's got the same neighbor within a solid. And then the last one would be a gas. The big difference between liquids and solids, again, molecules are really close to one another. The difference between a solid, solids are stuck in place, liquids are tumbling around. In a gas, these molecules are very far apart from one another. They're completely sort of free and independent. They only ever kind of collide with their neighbors very randomly. But yeah, so the distance between molecules is really far within a gas. And they will, not only do they take the shape of their container, they'll actually expand to fit the entire container. All right, so if we look at our periodic table, this is sort of at room temperature. how do we find a pure sample of each of our elements, right? So the yellow is solid, the blue is liquid, and the green is gas. Notice that most elements are a solid at room temperature. So for example, if I had a pure sample of carbon, that would be a solid. That's actually like a graphite from the tip of your pencil would be a pure sample of carbon. Likewise, if I had a pure sample of iron, that would also be a solid, that block of metal. Other substances are liquids at room temperature. There's actually only two of them that are liquids at room temperature. Mercury, which is kind of special because mercury is a metal, is a liquid at room temperature. You know, old thermometers would have used mercury. And then bromine is also a liquid at room temperature. Those are the only two. Liquid bromine is sometimes used, I don't know if it is as commonly anymore, but was used to sanitize skin, kind of like an antiseptic before surgeries and stuff. And then we have a few molecules that are, a few elements rather, that are gases at room temperature, right? So we know we have oxygen, which we know we need to survive, is a gas at room temperature. Actually, the air we breathe is composed, it's a mixture of both oxygen and quite a bit of nitrogen as well, which is a gas at room temperature. So these elements would appear as gases. If we had a pure sample of oxygen or a pure sample of nitrogen, it would be in the gas form. So this periodic table is a little bit of a cheat sheet for which elements are what at room temperature. Okay. You know, what we do a lot in science is to characterize substances by their properties, and we can do so in like one of two ways. We consider this. One is to do so quantitatively, so these are measurements that involve numbers. And the other thing is to do so qualitatively. So we were just qualitatively discussing the state of matter, a solid, a liquid, or a gas. That would be a qualitative property. If we measured the volume of our gas at 1 liter, that would be a quantitative measurement. The other distinction that we're going to make here is this idea of a physical property or a physical change versus so physical property versus a chemical property. Physical properties are something that can be observed and measured without changing the identity of the substance, right? So if we took the mass, or even if we took a boiling point, right? So we took water from being in the liquid phase to the gas phase, that would be boiling. We don't change the fact that water's water when we do that, right? Same sort of idea. You take you fill up your ice tray with liquid water and you put it in the freezer, it goes from being a liquid to a solid. That would be a physical change because, again, you're not changing the identity of that water. Okay, it's still water in both cases, it's just the state of matter has changed. A chemical property or a chemical change is something where basically chemistry is occurring, bonds are being made and broken. You're changing the identity of that molecule, right? So for example, the rusting of a metal is actually, if you're rusting a metal, you're going from iron to iron oxide. Whoops, I guess it's pretty much that, yeah. To iron oxide, you're actually changing the identity, the chemical formula of what's going on there. Right? So a chemical change is going to be anything that messes with the chemical properties of that molecule, any sort of reaction that's occurring. In chemistry, we say that a chemical reaction means that bonds are being made or broken, right? So if there's any sort of a chemical reaction going on, that would be a chemical process. All right, so sort of sample problems that I could ask you from this particular lecture would be something like, let's classify these mixtures as being a pure substance, or let's classify these these whatevers as being a pure substance or a mixture. So an aluminum in a soda can, okay, is that a pure substance or a mixture? A soda can is actually made of just pure aluminum that's been rolled up into this particular shape. So that would be a pure substance. What about a sports drink like Gatorade or Powerade? right? We all know that these aren't just water. They contain things like, you know, certain electrolytes as well as sugar, some flavoring ingredients, probably some fake color ingredients going on there. So these would be a mixture. And we can actually go even further. What about if is it homogeneous or heterogeneous? Powerade or like Gatorade, whatever, a sports drink would be an example of a homogeneous mixture, right? All those electrolytes, those sugars, those flavoring ingredients, those colored ingredients, they're all uniformly distributed around that liquid. So this would be a mixture that is homogeneous. Okay. Salt, what would table salt be? So table salt is composed of a pure substance of what's actually NaCl, sodium chloride. And we'll talk a lot about ionic compounds later in this lecture. But yes, so that is a pure substance. And what about carbonated water? I actually got some right here. We can see that that is a mixture. And actually, this is an interesting one in terms of homogeneous versus heterogeneous. If I let it sit, it's going to be a perfectly homogeneous mixture where the bubbles are, you know, the carbon dioxide that's dissolved in there is sort of uniformly distributed throughout. As soon as I shake it up though, that kind of changes a little bit. Now I have more of the carbon dioxide that's kind of at the top as opposed to the bottom. But we're going to assume when we ask these questions that they're after it sits, not, you know, when they're being jostled. So this is again an example of a homogeneous mixture. I guess we'll even say when still heterogeneous mix when disturbed. Okay, so classify pure substances or mixtures, and then we also have this idea of a chemical versus a physical property. Okay, so water has a density of 1 gram per mil at room temperature. Is that a physical property or is that a chemical property? Is there a way to measure that, right? Would be a physical property would be to measure it without disturbing the identity. Well, if I measure density of water, I don't change the fact that it's water. So this would be an example of a physical property. What about iron rusts in moist air? We actually sort of already gave this example, but this is an example of a chemical property because we're changing the chemical identity of iron. It's going from iron to iron oxide. So this would be chemical. Copper turning green over time. Okay, this is what's called, you know, basically the reason why copper is turning green is because it's not staying copper. Any sort of a color change like that is indicating that there's a reaction going on. So just like when iron turns red, when it rusts, copper turning green over time is actually also what we call an oxidation reaction, or a reaction between copper metal and oxygen to produce copper oxide. So this is again a chemical property, and any sort of a color change is indicative of chemical change, because you really can't change the color of something without changing its molecular composition. And aluminum melts at 660 degrees Celsius. Well, if I melt aluminum, am I changing it from being aluminum? It's still aluminum, right? So whether I melt it down into a liquid or I let it harden again into a solid, it still remains aluminum. So this is an idea of a physical property. Okay, and I guess real quick, I want to take this opportunity to point out that there is a difference between melting and burning. Melting is specifically a physical process because you're not changing the identity of something. You're melting ice, right? For example. It's still water at the end of the day. Burning is a chemical process. In both instances, you're heating it up, but when you're burning something, you're actually reacting it with oxygen, right? So if you imagine taking a piece of wood and throwing it on a fire, at the end of the day, you don't have wood anymore. You have this burnt mass of carbon. That's because you've changed the properties of that wood. It's no longer wood anymore, right? So that is a chemical process. So in both of these instances require heat, but they're very, very different from a scientific standpoint. One is a chemical process, burning, whereas melting is a physical process.